First, we will recap PN junction diode. The PN junction diode, what we will do, we'll take a silicon crystal. This is P type, this is N type. This is doped in such a way that half portion is P type, half portion is N type. And due to the concentration difference, electron will move from here to here and holes will move from here to here. So due to that, a depletion layer containing negative and positive immobile ion will form, and due to that the potential barrier will form. Okay, we discussed this potential barrier. This also we discussed. Now, effect of doping on the concentration means if we will change the concentration of holes, or if you will change the concentration of electron, so how the depletion layer will affect. So what is the depletion layer? Basically, the reason of formation of the depletion layer is the motion of electrons and holes due to the concentration difference. So if we suppose are increasing the concentration, if suppose we are suppose increasing the concentration, so more number of electrons will be there, more concentration will be there. If we are increasing the concentration of electrons, suppose, so more doping we are doing. More doping we are doing means more number of electrons will be here. Suppose we are doing doping in N type, so more doping we will do, more electron here will be there, and more concentration difference on both sides. So there will be the flow of more electron from here to here. What will happen? These electron will combine with this positive charge, and these holes, when moved from P type to N type, will combine with this negative charge. So what will happen? Neutralization will take place and depletion layer thickness will decrease. Depletion layer thickness will decrease, and if you will decrease the doping level, so the vice versa means the depletion layer thickness will increase. So that is what written here. If the concentration of a doping will increase, the recombination of electron with positive ion and holes will increase, the width of the depletion layer will decrease. If the concentration is decreased, the recombination will decrease and width of depletion layer will decrease. Forward biasing and reverse biasing, I told you, forward biasing and reverse biasing. So what is forward biasing? First, again we will see what is forward biasing. P type of P, this is a symbol of PN junction. So P type is connected with positive end of the battery. N type is connected with the negative end of the battery. And in forward biasing, more current will be there. More current will be there. Less potential difference, potential barrier will be there. In case of the reverse biasing, the negative of the battery is connected to P type and positive of the battery is connected to N type. Potential barrier will increase, less, and on very less current will be there. Or for ideal diode, we can say there will be no current in reverse biasing. So now we will discuss IV characteristics of the I means current and voltage characteristics of the forward and the reverse biasing. So VI characteristics. So this is a diode, PN junction diode. This is a PN junction diode, and here a voltmeter is connected. This is a voltmeter. Okay, this voltmeter is connected here. See, this is a PN junction diode. Okay, this is a PN junction diode. PN junction diode. Okay, this is P side, this is N side, and here a voltmeter is connected. A voltmeter is connected. So we know that voltmeter is connected in parallel. So this is the voltmeter connected, and here an ammeter is connected. Milliammeter is connected. Why we are connecting the milliammeter? Because I told you this in forward biasing. The current will be in milliampere in forward biasing. That is why to measure that current, we have to apply, or we have to connect it and connect it with a milliammeter. This is milliammeter, so it will measure the current in milliampere. And we know that the ammeter is always connected in series. Okay, so this is the battery and this is a variable resistance and this is the key. There is a potential difference across this battery, and this is the forward biasing, means this is P type, this is P side, this is N side. P side is connected to positive of the battery, N side is connected to negative of the battery, means this is forward bias, and here voltmeter connected, here an ammeter connected. Okay, this is a voltmeter. And this is ammeter. Voltmeter is used to measure the voltage, ammeter is used to measure the current, and ammeter is always connected in series, voltmeter is always connected in parallel. And this diode here is in the forward bias condition. So I told you that this potential will be from positive to negative, and this potential will be from N to P. That will be the potential barrier. In the last class, in case of the forward biasing, you can see here from N to P, the direction of the, we just take the direction of the VV, means potential due to the diode in this direction from N to P. Okay. Always remember in case of the PN junction diode, the potential direction you will take, okay, you will draw the battery like this, corresponding to this PN junction diode. Okay, so potential will be in this direction, V. Potential you will represent like this, positive, this will be positive, this will be negative. So in this direction, so both are in opposite direction, so the potential barrier will decrease. I told you in forward biasing, it will become V minus VV, potential barrier. For example, if the applied V is the applied voltage, V is the applied voltage. V is the applied voltage. So, for example, if suppose applied voltage is, if this potential barrier is 0.7, suppose, see here, this side, suppose the potential barrier is what, 0.7 volt, and applied voltage is, suppose you are applying 0.5 volt. So net voltage will be V minus VV. If you will take the magnitude, it will be, net will be come out to be minus 0.2 volt. So 0.2 volt it will come out. Okay. So means now also there will be some potential barrier. Okay. Less current will be there. Suppose if you have applied 8 volt, 0.7 volt you have applied. So what this difference will become? It will be 0 volt. Now there will be no potential barrier. No potential barrier will be there. This is just the example I am giving. So if no potential barrier will be there, majority charge carrier will flow. There will be the flow of majority charge carrier inside this PN junction diode. More will be the current. So there is a particular voltage at which the current will suddenly increase. After a particular voltage, initially when you will increase the applied voltage, and when this applied voltage which will reach to a specific value, the potential barrier will cross and current will become maximum. Why? Because now the majority charge carrier can flow. So this type of graph we will get. This type of graph we will get. This is the knee voltage. So now this is the current. IF means the forward current. IF means the forward current here. IF is representing forward current. Forward current means current in forward wise. You can say current in forward biasing. B suffix F means current in voltage in forward biasing. Applied voltage you can say. Voltage. Voltage in forward biasing. And this will be the net voltage, not the applied voltage. So when this net voltage will become a specific value, this is for this diagram is for basically silicon. Okay, this graph is for silicon, because silicon is having 0.7 knee voltage. So now see from starting, you are applying the voltage, you are increasing this value of V, you are increasing this value of V. So potential barrier is decreasing, current will increasing little bit. So from here the current will increase. From A to B you have applied the voltage, potential barrier is decreasing and current is increasing little bit, and again you have applied, again you have again you have increased the applied voltage, potential barrier will again decrease, B minus BB it will again decrease, and value will reach here at the knee voltage, then potential barrier will become 0, and potential barrier will become 0. Now maximum number of charge carrier will flow. There will be a flow of maximum number of charge carrier, and the current you can see suddenly increase, and this current will be in the milliampere VI characteristics. Any other things there? No. Okay, Nafisa, understanding what I told you?
Yes, sir.
Okay, so we will write now theory. Number one, point number one. Initially, the current in the circuit is negligible. The current in the circuit is negligible. Till the voltage reaches knee value. Till the voltage reaches knee value. Or cut in voltage. Knee value, or this is also known as cut in voltage. Knee value or cut in voltage. That is 0.7 electron volt for silicon and 0.3 electron volt for germanium. Okay. Now, before cut in voltage, the depletion layer plays a dominate role plays a dominate role in providing barrier to the majority charge carrier. To the majority charge carriers. So it means the same thing. Initially, when the voltage, applied voltage or the net voltage will be below knee voltage, okay, thickness of the depletion layer will be more. Thickness of the depletion layer will be more, or it will provide a barrier to the majority charge carrier, and motion of majority charge carrier will be less, and that is why the current is less. When we will reach at the knee temperature, knee voltage, potential barrier will vanish out, and now the charge carrier can flow easily and current will suddenly increase. Point number second, once the voltage reaches the cut in voltage, or you can say on reaching the knee voltage, on reaching the knee voltage, the current increases exponentially. The current increases exponentially. Exponentially means very fast. Exponentially means you can say sharply also. Sharply. Even for a very small change in applied voltage, even for a very small change in applied voltage, at this stage, at this stage, for the majority charge carrier, for the majority charge carrier, there is negligible resistance at the junction. There will be negligible resistance at junction. So again, what will happen when the net voltage will become the knee voltage? So the potential barrier will become zero. Potential barrier will become zero, and potential barrier will become zero. So we can say now the charge carrier can move. Majority charge carrier now can move from P to N side or N to P side. So thickness of the depletion layer will decrease, and you can say the resistance will decrease for the majority charge carrier. And basically, you can say there will be the negligible resistance for the majority charge carrier to flow, and that is why the current will become maximum when you will apply a small voltage, which is small, which is just greater than the knee voltage. Now we will discuss the VI characteristics of the reverse biasing. What will happen in reverse biasing? In reverse biasing, the potential barrier will increase, and when potential barrier will increase, what will happen? Charge carrier cannot flow, and depletion of the thickness of the depletion layer will increase, and resistance for the charge carrier will increase, and current will become very less. But there is a voltage at which the breakdown will take place and current will sharply increase. You can see here. Okay, now we are discussing the VI characteristics of reverse biasing. So here a voltmeter is connected again. Voltmeter, and here a micro ammeter is connected. Why micro? Because in case of the reverse biasing, microampere current will be there. You can see here. Current is in microampere. So that is why you have to connect a microampere in series. Microammeter in series. Microammeter means microammeter measures the current in microampere. Microammeter measures the current in microampere. Okay. Okay. So this is so now this is a reverse biasing. Negative terminal is connected to P side, and positive terminal of the battery is connected to N side. And what is the direction of potential difference? What is the direction of the potential here? From N to P means in this direction. VV. And here also the applied voltage will be in this direction. So they both will be added up. So this potential barrier will increase now. Potential barrier will increase, and potential barrier will increase, current will decrease. So this type of graph will have this graph will be in the third quadrant. So IR means the current in reverse bias, reverse current in reverse biasing. IR means current in reverse biasing, and VR means net voltage in reverse biasing. So basically this type of graph you will get. Initially when you will apply the voltage, so the potential barrier will increase. Here the potential barrier will increase. So when you will apply the voltage, but here na in case of the basically here this is the graph in the third quadrant. Okay, this is third quadrant. So when you will move from here to here na, so the potential will increase in negative direction. So initially there will be zero current, and if you will increase this voltage V negatively, okay, if you will increase, suppose we know that VV for silicon is equal to what value? 0.7 na? 0.7 electron volt for silicon. So to make this zero, what you have to? You have to apply the negative voltage. So negative voltage you are applying, and current will remain constant till the breakdown voltage. And when you will reach at the breakdown voltage, the current will suddenly increase. Okay, current will suddenly increase. So in this we can write number 1, when diode is connected in reverse bias, when diode is connected in reverse bias, the current remains almost constant. The current remains almost constant with biasing. And this current is called reverse saturation current. And this current is called reverse saturation current. Reverse saturation current. We are talking about this current. This is the reverse saturation current. And it is due to the flow of, and it is due to the flow of thermally generated charge carrier. Thermally generated minority charge carriers. Thermally generated minority charge carriers. What are they? Holes in p types. We know that. Okay, so we can write here holes in p type and electrons in n type across the junction. So in reverse biasing, what will happen? Current is zero initially. Initially, we are assuming this diode as a ideal diode, so current is initially zero. But we are now applying the negative voltage. So negative voltage we are increasing. The current is constant. This current is reverse saturation current. This constant current is known as the reverse saturation current, IS. IS is reverse saturation current. Current. After a certain voltage, that is known as the breakdown voltage. Basically, this is known as the Zener breakdown voltage. So you can say breakdown voltage. Suddenly the current will increase. Suddenly the current will increase. So next point number 2. When a reverse when a reverse voltage reaches, reverse means negative voltage, reaches a sufficient high value, sufficient high value, the current increases rapidly. The current increases rapidly. Increases rapidly, and this voltage is known as breakdown voltage, and this voltage is known as breakdown voltage, or this is also known as Zener breakdown voltage. Zener breakdown voltage. Zener breakdown voltage. As the value of this voltage is as the value of this voltage is 1 to 1 is 1 to 2 volt to several thousand volt, several thousand volt. It depends upon the doping concentration. It depends upon the doping concentration. So what is here? You can see what you are doing. You are increasing the voltage in the negative direction, means reverse voltage you are increasing. So this potential barrier will decrease. So after a certain negative voltage, this value will become 0, and then again there will be a condition of breakdown, and the current will suddenly increase. Okay. So after this, we will discuss the rectifier. After this, we will discuss the rectifier. Diode as rectifier. Okay. So the topic is diode as rectifier. So we will see what is rectifier. Nafisa, do you know what is rectifier? Hmm? So, so what is rectifier? First, we will see. So basically, rectifier, a device that converts the AC to DC. Okay, it is a device used to convert alternating current to direct current. To direct current means AC is converted to DC through rectifier. Two types of rectifiers are there. Number one, half wave rectifier. Number 2, full wave rectifier. Have you heard this name, Fiza?
Yes, sir.
Half wave and full wave rectifier. So basically, rectifier is a device that converts the AC to DC, alternating current to direct current. So now, why I have written diode as a rectifier? Because why I have written diode as a rectifier? Because with the help of diode, it will convert AC into DC. We will see that. So diode as a rectifier is an important topic. So first you should know what is the rectifier. Okay, types of rectifier, half wave and full wave rectifier. First we will discuss the half wave rectifier, and after that we will discuss the full wave rectifier. So before that we should know what is the principle of the rectifier. What is the principle? Principle of rectifier. Like the principle of electric generators is electromagnetic induction. Means whenever the magnetic flux linked with the coil changes, an EMF will induce according to the Lenz law. According to the Faraday law, sorry. Okay. So principle of rectifier for an ideal diode, for an ideal diode, the diode will conduct during forward biasing. The diode will conduct during forward biasing and it will not conduct during reverse biasing. And it will not conduct during reverse biasing. So when the diode will be forward biased, current can flow through it. When the diode will be reverse biased, no current will flow through it. So half wave rectifier is this. This is the half wave rectifier. Now this is a primary coil, this is a secondary coil. Primary coil, secondary coil. Basically this here is a transformer. This is a transformer, and in transformer we have primary coil and secondary coil. So you have understand in this way, a primary coil is there, a secondary coil is there. Primary coil means this is a primary coil. Primary coil means this coil is connected to an AC supply. This is an AC supply. What supply? AC supply. AC supply is there to the primary coil. Means there is a AC supply means how we represent AC, alternating current, like this. Like this, no? And this is positive cycle, negative cycle, positive cycle. Voltage versus time graph. I told you in AC. So we are supplying this type of voltage. Positive cycle, negative cycle, positive half, negative half, positive half. This is primary winding, secondary winding, primary winding. This is secondary winding. Secondary winding. windings. So now we will discuss the working. Working is very simple. During the positive half cycle, take 2 points. Suppose this point, suppose this point as A point, and this point is taken as B point. This point as A point, suppose this point as A point, and this point as B point. So what will happen during positive half cycle? During positive half cycle, first this will become plus and this will become negative during positive half cycle. Just imagine this is plus. Polarity will change because alternating current you are providing. You are providing the alternating current. That is why polarity will change. First it will become positive. This end will become positive. This end will become negative. After that, this will become negative. This will become positive. Suppose initially this is positive. So this A is positive. A will be positive. Suppose A will be positive. So here also this will be also positive. This end will be also positive and this end will also be positive end. So consider this end as A and B. It will be better. This is A and this end as B. So actually now what will happen? Mutual induction will take place when this will be positive. So this will be negative. This I am removing. Mutual induction process will be there. So this will be positive. So this end will be positive. So due to the mutual induction, what will happen? If this will be positive, then this will be negative. So basically, I want to say that during the positive half cycle, suppose this end is positive. At any time, this ends become positive and this end become negative. Okay, this end becomes negative. So this is positive. Positive end means positive is connected to P side and negative is connected to N side. Means this is a condition of forward biasing. So in positive half cycle, the diode is forward biasing, means the diode will conduct. So current will flow through the load and we will get the output here. We will get the output here. So this is RL. RL means load resistance. RL means load resistance. So we will get the output through this. For the negative half cycle, so what will happen? Negative half cycle, this end will become negative and this end will become positive. So means now you can see here, negative is connected to P type and positive is connected to N type. So diode will be reverse biased. No current will flow through load. No output we will get. So the polarity will change. Okay. So in theory, I will write that. So you have to remember that. Okay. You are supplying AC. So due to the mutual induction, in this also there will be the induced current and the direction of the induced current is opposite to that of applied current. So I am not going in that. Basically, how the mutual induction will take place, that is a different process. But here we have to understand that when we will supply AC during positive half cycle, when this will be positive, suppose. So it will be, this diode will be forward biased and the current will flow through this diode and current will flow through the load and we will get the output when this end will become negative, because every time after a certain period of time the polarity is changing. Okay, polarity is changing. So polarity is changing. When this will become negative, so this diode will be reverse biased. When this diode will be reverse biased, no current will flow, no current through the load, no output we will get. So now working of half wave rectifier. So during positive half cycle, and A is positive, and A is positive, and B is negative, and B is negative, and diode is forward wise, diode is forward wise, hence current flow across the load, current flows across the load, and we will get the output, load resistance, you can say, RL. Okay, now during negative half cycle, and A, so during negative half cycle, this and A will become negative. So and A will become negative. So this diode will be reverse biased. No current will flow. No current will flow through the load also. So and A is negative, and B is positive. Positive. And the diode is reverse biased, and the diode is reversed bias. No current flow through the diode. Through diode. And no output is obtained. Or you can say no current will be there through load resistance and no output will be there. And no output will obtained. So basically this type of input you are giving. What type of input you are giving? You are giving the input like this. You are giving input like this, and like this, and like this. So this is positive half cycle, negative half cycle, positive half cycle, negative half cycle. So you are getting output only positive half cycle. So your output will be like this. Your output will be like this. Means during negative half cycle, you will get no current. So negative portion will be removed. Okay. So this will be your output. So if the frequency of this suppose is 100 hertz, so the frequency of this will be also 100 hertz. Frequency means number of waves in 1 second. Number of waves in 1 second. So from here to here, suppose there is 1 second. So one wave is completed. From here to here, suppose 1 second. So one wave is completed here also, na? That is why the frequency remains same. So frequency of input and output remains same. frequency of input and output remain same. Okay. This is half wave rectifier. Now we will discuss the full wave rectifier. So full wave rectifier, in full wave rectifier, instead of one diode, there will be two diodes. There will be two diodes, and load resistance is connected like this. Load resistance is connected like this. Okay. This is primary winding. This is secondary winding. P. Okay. This is S. S. P means primary winding. S means secondary winding. Windings. And N1, you can say the number of turns in this winding, N2 is the number of turns in this winding. So mutual induction will take place. Again, take this point as A and take this point as B. So from here you are applying an alternating voltage like this. Positive half cycle, negative half cycle, positive half cycle. So this is the AC supply. Alternating current supply. Supply is there. So when this A end will be positive, so this diode will be connected with positive end will be, when this A will be positive, this diode is connected with positive end in wait. Okay, now we will see. When this A is positive, so this positive is connected with P type, and negative, this B end is negative, negative is connected with N type. So this diode will be forward wise. So in this diode, there will be a current during the positive half cycle. Now during the negative half cycle, suppose this B becomes negative, B becomes positive, and A becomes negative. So now this D1 is reverse bias because negative is connected with P type and positive is connected with N type. So this D1 is reverse bias, but now see D2. Positive end is P type is connected with positive end and N type is connected with negative end. So this diode during the negative half cycle will be in the reverse bias, and this diode will conduct, and again you will get the output. So during the positive half cycle also you will get the output. During the negative half cycle also you will get the output. Understanding? Understanding
Yes,
or
sir.
not? Okay, so okay, wait. Azan time is there, so we will wait for 1 minute. Then we will continue. Okay. So working, you can write the working. During positive half cycle, this diode is forward bias. During negative half cycle, this diode is forward bias. Means during positive half cycle also, during negative half cycle also, we are getting the output. So how input and output will be there? So input will be like this. Again, input will be like this. This will be the input. This is the input. And how the output will be, because now you are getting output for the positive half cycle also and for the negative half cycle also. The output will be like this. Suppose 1 2 3 4. So during the negative half cycle also you are getting the output now. So this will be like this. Okay, so okay, like this. For positive half cycle, this is the output. For negative half cycle, this is the output. So, but in this case, you have to think. You have to think. Now, from here to here, one wave is completed. Suppose from here to here, there is 1 second or time period t. From here to here, the time period was t na? And from in this case, from here to here, the time period was t. So in time period t, only one wave is completing. Here in time period t, two waves is completing. So the frequency of this will become double. Frequency is what? Number of waves completing in 1 second. So if frequency here 100 volt, 100 hertz, so here the frequency will become 200 hertz. So you can say that frequency of output will become double of input. Now the last topic of our syllabus is filter circuit. So filter circuit is nothing. Basically what happens, the DC we are getting the output na, in this form we are getting output. This is the output, DC output. So basically this is in the pulsating form. There is some component of AC also in this. So we have to filter that AC component from this DC so that we will get the pure DC. AC filter circuit means that will filter the AC component from the output. So what we will do now? Here we will connect this load resistance with a capacitor. And we know that capacitor blocks DC. We know that the capacitor will block DC if the current, suppose going, this is the output current. This output current is containing AC plus DC. AC plus DC containing. But in this capacitor, DC cannot flow. So in this capacitor, what will go? AC will go in this capacitor. And whole DC will go through load resistance. No, it is not clear, I think. It's not a clear diagram. See, this is the full wave rectifier now. So what we do, we will connect here, we will connect this with a capacitor, okay, in parallel with the load resistance. So now, suppose this is the output current. I is the output current, and this I is containing the AC component also of current plus DC component of also DC component also. So now in capacitor we know that the DC current cannot flow, because why the DC current cannot flow, you can see XC is equal to 1 upon omega C. Omega is 0 for DC. So the capacitive reactance will become infinity. Means infinite reactance will be there for DC. That is why DC cannot flow in capacitor. So in capacitor, what will flow if DC will not flow? Whole AC will flow through capacitor, and whole DC will flow through the load resistance. Means we will get pure output of DC. Pure DC we will get. So what is filter circuit now? Filter circuit. Filter circuit, the output obtained from the rectifier Hello, Nafisa. What happened? Is there any problem with my internet or your?
No, my net. I'm sorry.
Okay, no problem. It's fine. So, till where I told you? Have I told you the filter circuit? Have I started the filter circuit? No.
No, sir.
Okay. Have we completed the full wave rectifier or not? This one
Yes, sir.
means this whole we have completed now.
Yeah.
Okay. Are you sure? Okay. So now basically what is happening in full wave rectifier? This is a full wave rectifier. So during positive half cycle, we are getting output. During negative half cycle also we are getting output. But this is not a pure DC. Some AC component is also there in this. So we want to filter that DC AC component from this so that it will become pure DC. That is why we are using the filter circuit. Now see what is the work of the filter circuit. Again I am telling. Okay, now see. This is a full wave rectifier. Okay, this is what? This is full wave rectifier. This is full wave rectifier, and I told you the working of full wave rectifier. What will happen during positive half cycle? This will be forward wise. This will conduct. So there will be the current through the load, and we will get the output during the negative half cycle. This will become forward wise, and this will become reverse wise. This will conduct. So through this circuit, there will be the current through the load resistance, and again we will get the output. Means during the positive half cycle, we are getting the output. During the negative half cycle, we are getting the output. So during both the cycles, we are getting the output. But the output current we are getting is not purely DC current. That contains some component of AC. So we have to filter the AC component with the filter circuit. Now, what is filter circuit? Filter circuit is nothing but we will connect a capacitor in parallel with the load resistance. This is the capacitor. And we know that in capacitor, we know that the capacitive reactance of the capacitor is equal to 1 upon omega into C, and omega is 0 for DC. For direct current, the omega is 0. So Xc will become infinity. Xc will become infinity means infinite. You can compare it with an means you can compare it with a resistance. Infinite resistance is there, or infinite reactance is there for DC. So through capacitor, DC cannot flow. So what will happen? Suppose this is the output you are getting, output current, and this output current containing AC component plus DC component. Okay, so AC component, DC component cannot go through the capacitor. So whole AC will go through the capacitor, and whole DC will go through this part, through the load resistance. DC will go, and the current which are going through the load resistance is the output. So output we are getting pure DC this time. So now input and output will be like this. So what I was telling you, the definition part. So the definition was filter circuit. Filter circuit. So the filter circuit is filtering the AC by using a capacitor in parallel with the load resistance. So the output we are getting, the output obtained from rectifier is unidirectional but pulsating. To get pure DC, filter circuits are used. Filter circuits are used. So basically this figure, should we blow this definition? No, it is fine. This type of filter is known as the shunt capacitor filter. This is shunt capacitor filter. Shunt capacitor filter. Now we will write some theory for it, then we will finish it. And what type of output we will get? Output we will get this type of output we will get. Basically, output we will get a pure DC. Pure DC is like this. This is pure DC. Okay. So now to filter circuit, to filter AC current, to filter AC current component, to filter AC current component. From the output, obtained by rectifier, obtained by rectifier, we need to connect a capacitor. We need to connect a capacitor. Connect a capacitor in parallel with load resistance, parallel with load resistance, and capacitor offer infinite resistance. To DC, and pure DC will flow across resistance. Pure DC will flow across load resistance. So now this chapter is finished. Okay, and that is about the semiconductors. And so now you should take these screenshots.
Okay, sir.
Yeah, I'm zooming in. Yeah.
Done, sir.
Okay.
Done, sir. Done.
Okay.
Done.
Okay.
Done. Done.
Okay. So this is a rectifier. Just a minute. Now take the screenshot.
Done.
Okay. Take this screenshot.
Done.
Okay. Take this screenshot. Working.
Done.
Okay.
Done.
Now full wave rectifier. So theory you can write during for when this A will be positive, this will be forward wise and this will be conduct. Okay, and when B will be positive, so it will conduct. Okay, so during positive half cycle also we will get the output. During negative half cycle also we will get the output. Okay, now take the screenshot.
Okay. Okay, sir.
Done. Okay, please take.
Yes, sir.
Okay. Now this is the input and just a minute. This is the output. Output. Okay. Now you should take the screenshot. And remember that frequency will become double in case of the full wave rectifier because number of waves in 1 second will double or number of waves in a particular time period will become double. Done?
Yes, sir.
Okay. So filter circuit is there. Take this screenshot.
Done. Done, sir.
Okay. 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 Take this screenshot. Done? Nafisa completed? Completed? Hello? Hello, are you getting my voice? Okay. So now getting my voice?
Yes, sir.
Okay, so have you completed this one?
Yes, sir.
Okay, so please take this screenshot.
Done.
Okay, so now just a minute. Okay, take this screenshot. Oh, sorry. Take this screenshot.
Done.
Okay, so Nafisa, that is all about the syllabus. So this is finished now. So now, when will be your when will be your exam?
Physics exam or the starting of my exam?
Start